Okay guys, let's have a little look at the intro for this section now. 25 questions or something on matrices. Here's the root map. I've drawn a little thing what we need to do. It's quite a lot to get through here, so I'll do it as succinctly as I can. So here's the root map. First of all, we're going to look at transpose, because where are we heading? We're heading to the end of this route, to the inverse. We want to find the inverses of both 2x2s and 3x3 matrices. And here's the route through, okay? The first thing we're going to do is we're going to find out what transpose is and how to transpose a matrix, both 2x2s and 3x3s, or any other size for that matter. And then we're going to go from there and we're going to work out determinants of 2x2s and 3x3s specifically. And we'll find out what the determinant is. From there, we'll look at the cofactors, a cofactor matrix, and that will be in the 3x3 case. And then we'll go up to the adjoint, something called the adjoint of a 3x3 matrix. And then from the adjoint, we can get to the final destination of finding an inverse of a 3x3 matrix. And there's a detour. You'll notice we just carried on looking at the 3x3 case here. So at the very end, we'll do a little detour because it's quite straightforward of how to obtain the inverse of 2x2 matrices as well. Okay then, so I thought I'd give you a route map to show you where we're going. Okay, first of all, transpose then. What is transpose? Well, what you do here is you flip around the matrix. So you either flip around the rows to columns or columns to rows. So in other words, your first column becomes your first row, and your second column becomes your second row. So let's do that, shall we? So the first column is 2, 4, minus 6, and I'll put it in first column, change that first column to the first row. 2, minus 4, and 6. And then the second column becomes the second row. And we just changed the rows to columns. So this would be the transpose. So that transposed is equal to this matrix. So let's take the same matrix again, and instead of transposing the columns, let's transpose the rows. So first row goes to first column. So there's a 2 and a 3 there, yeah? Second row goes to second column. And the third row goes to the third column. Can you see they're both the same? So you take your choice. You pay your money, you take your choice. Whatever you prefer to do, and whatever looks easier on the eye to you, do to obtain the transpose. So you flip the rows to columns or columns to rows. So transpose is done then. So the next thing is the determinant, both of a 2x2 and a 3x3. The 2x2 case, the word determinant really is akin to determining whether the matrix has an inverse, and we'll get to that in due course. Notation, we usually write matrix A with vertical lines either side, and that is a notation for the determinant, or we can write simply det A. Either of these, and you can write them both on the same page if you wish. Sometimes you'll write one and sometimes you'll write the other, depending on the context of the problem perhaps, or what your preference is. There's no problem with that. So the 2x2 case then, the simple rule for 2x2s, it's going to be the leading diagonal product, take away the trailing diagonal product. So let's have a go at that then here. Okay, leading diagonal is 3 times 6, yeah? So 3 6s are 18. Take away the trailing diagonal, which is 1 times 4, which is 4. 18 take 4 is 14. There we go. That's the 2x2 case. Leading diagonal, take trailing diagonal. Very easy to do for determinants in the 2x2 case. So let's go on then. And now we'll look at the 3x3 case then for determinants. And basically, it's a bit more involved. You run along any row or column and multiply each element with their respective minors. And combine minors, and combine with a sign according to this rule here. Plus minus plus, minus plus minus, plus minus plus. So I'll illustrate that here, and we'll run along the top row, okay? Because it's best explained by examples. So if I put, I'll choose a different color. So if I put a plus, minus, and plus, so according to this rule here, I'll put them there. So it's plus 1. Everyone okay with that? Yeah, 1. And then you cross out the row and column containing the 1. Because you multiply each element with their respective minors. The minor is obtained by eliminating the row and column containing the entry 1, and you're left with this 2x2 here. 3, 1, 6 minus 2. So it will be 1 times that minor. So I'm going to need a vertical line here. to denote the minor. Okay, so it would be 3, 1, 6 minus 2, and then it's minus minus, so combine that and make a plus 4. Cross out the row and column containing the 4 and write down the associated minor, which would be 2, 1, 4 minus 2. See here? 2, 1, 4 minus 2. And then the last entry, plus and a minus is a minus, the 7. And then our 2 lines. And then cross out the row and column containing the 7, and you can see we're left with these 4 entries here. 2, 3, 4, 6. 2, 3, 4, and 6. So what have we got then? We've got 1 times minus 6, agreed? Because we're doing the determinants of these 2 by 2s now. Minus 6, take away 6, plus 4. Minus 4 is the leading diagonal product. Take away the trailing diagonal. 1 times 4 is 4. Minus 7. Leading diagonal is 12. There. Minus the trailing diagonal, which is 12. Okay, so what have we got then? We got one lot of minus 6, which is minus 12, times 1 is minus 12. This is minus 8, times 4 is minus 32, plus the minus is a minus. 12 take 12 is 0, 7 noughts are 0. So you end up with minus 44. Yeah? And that was obtained, this 3 by 3 case determinant was obtained by running along the top row, wasn't it? Well, let's do it differently, shall we? Let's run along and see what we get for the determinant if we run along the first column then. Because we did say here that we could run along any row or column. So I'm going to associate the signs again, and I'm going to do it here. And I can do it a little bit quicker this time. So here the determinant is equal to then, let's run along this row, plus 1. And then you can see cross out the row and column containing this, and you're left with 3, 1, 6, 2. And that is leading diagonal product, minus 6. Take away trailing diagonal product, which is 6. Yeah? Then you've got minus the 2. Cross out the row and column containing the 2. You're left with these 4 entries. Minus 4, 7, 6, minus 2. The leading diagonal product is 8. 4 2's with 2 minuses is 8. Take away minus 42. That'll be plus 42. So you've got 8 plus 42 is 50. So let's just write that down. 8 plus 42, wasn't it? And then the last one is plus 4. Cross out the row and column containing the 4. And these are the 4 elements. So you've got minus 4. Take away minus 21. So that'll be plus 21 now, won't it? So let's see what we get. See if we get the same, because we've said we should get the same. 1 times minus 12 is minus 12. 8 and 42 is 50. Minus 2 times 50 is minus 100. And here we've got minus 25. Minus plus 17 times 4. Yeah? Plus 17 times 4 is 68. So I wonder if we've got it. I've been trying to work it out in my head to see if we have. 17 times 4 is 68, yeah? 68 take 12 is 56. And 56 take 100 is minus 44. You can tap it in the calculator if you need to. So can you see I've illustrated it there? You can run down any row or column. It could be the middle one here, or this one here, or the one on the right hand side. And you adopt the same process and you'll get the determinant here. Okay then? So that's that done then. Good. So now, what do we need to do now on our root map? So we've done the 3 by 3 determinant. We need to go next to the cofactor matrix, don't we? So let's have a little look at the cofactor matrix, shall we? That's the end page. So the cofactor matrix then, here we go. You need to write a template like so. Best explained by examples rather than just a long description. Here's a matrix here. What you do is you write this template. Again, you write the plus minus plus minus plus minus plus minus plus. These entries consist of the associated minors. Right, these entries here. So that for the one element, which is in this position here, you cross out the row and column. So the 1, yeah, you cross out the row and column containing the 1 here. Or this element here. So here's the row and column containing the 1. And you've got 3, 1, 6, minus 2. And that's what you put in there. 3, 1, 6, minus 2. And then you move along the 4. Row and column containing the 4 is here and here. So you're left with 2, 1, 4, minus 2. 2, 1, 4, minus 2. And then you move along to the 7. Cross out the row and column containing the 7. And you're left with these elements. 2, 3, 4, 6. And then you proceed like that. Yeah? Okay, so shall I work through it a bit more? So this one here, row and column containing the 2. You're left with these 4. These 2 and these 2. Minus 4, minus 7. And then 6 minus 2. And then the middle one, cross out the row and column. You've got 1 minus 7, 4 minus 2. And then this one here, row and column, you'll have 1 minus 4, 4, 6. Yeah? And then this one here, row and column, and you'll have minus 4, minus 7, 3 and 1. And this one here, row and column, you'll see that it's 1 minus 7, 2 and 1. And then the last one here and here, you're left with 1 minus 4, 2, 3, aren't you? And this is the cofactor matrix. So we could write down the cofactor now here, C, and you just work out these entries. So this one, for example, would be minus 6 takes 6. Plus, so that's minus 12, plus the minus is a minus, so you end up with minus 12. So that would be minus 12, yeah? Okay, next one would be minus 4, minus 4. See it? Minus 4 is minus 8. Minus 8 is plus 8. And then this one, 12. Take away 12 is 0. Plus 0 is still 0. And you proceed like that. So you'd get all these entries here, here, and here. Here, here, and here. And then that's the adjoint. That would be the cofactor matrix. So the next thing in our list, once we've got the cofactor, which you proceed like that, is the adjoint. Yeah? Now the adjoint's fairly easy. So the adjoint is just the transpose of this matrix. So C transpose. So you transpose your matrix, your cofactor matrix. Okay, and that's easy to do. So you'd end up with a matrix. So this row, first row would be the first column. The second row would be the second column. The third row would be the third column. I might do a little bit more of that in a minute, but we'll see how we're getting on with time. Okay then, so that's C transpose. Now we're at the end of our destination because we got the cofactor. We transposed it, so that was the cofactor matrix C. And then the adjoint was C transpose. And now we can write down the inverse at long last. Yeah? So the inverse is here. And all it is now we've got the adjoint, which is denoted by Aj. We can just write the inverse. It's 1 over det A times Aj. And here's the point. If the determinant is 0, then the inverse won't exist. So that, by necessity, has to be non-zero, doesn't it? Because you can't divide by 0. So once you've worked out your determinant, it will tell you whether you have an inverse or not, and whether the matrix is invertible. Okay then, so there's your inverse. That's the end of the root. I think I've said enough about all this stuff now for us to work our way through the examples and do it and it's best explained by that way anyway. But come back to this if you just want to be reminded of exactly the processes involved, yeah? So let's just do that tiny little detour at the very first, at the end of the thing. A little detour of inverse of 2 by 2s, because this is an easy case. Right, all we do is a 2 by 2 matrix. And what we have to do here is we swap the leading diagonal around. So minus 7 and 2 get swapped. And then flip the signs of the this is the leading diagonal. And then the trailing diagonal, which is this one, what you do is you flip the signs of the elements. So because that's a 3, you flip it to minus 3. Because that's a 4, you flip it to minus 4. So that is, I've just done that wrong there, because that should be below, shouldn't it? So this is now, and divide through by the determinant. So this actually, let me just get rid of that. This is the, you flipped it around, and then you divide by the determinant. So let's just do that. Let's work out the determinant. So what have we got then? So, right, okay. So the determinant We know what the determinant is. You just work out the leading diagonal, minus 14. Take away the trailing diagonal, which is minus 12. Minus 26. There we are. There's the determinant. A to the minus 1 is 1 over det A times this matrix that you've just done. Okay, that's the formula. So we did that process and we divided by the determinant, which is minus 26. So we claim the inverse then. Minus 1 equals minus 7 minus 3 minus 4, 2. And there's 1 over 26 times that, so I'll put that here with a minus, okay? So that's what we claim the inverse to be. So you can check that. All we always do is we always check. Well, it's good practice to check that you've actually obtained it correctly without making mistakes. Okay, but I'll leave that for you to do, and it's also done many, many times in the examples as well. Okay, then that finishes the section. Sorry it's so long to explain all these things, but there's quite a bit to do in this section. So all the best, and I'll catch you again in the next section after you've done this one. Cheers!